this should be working. So we got the ChatGPT is going to be providing the intro for this, since ChatGPT is my co-host, kind of. Volume seems a little low. Okay, let's see. Test. Yeah, I don't know. I'll if anyone says it's low, then I'll turn it up, I guess. So here's the intro from ChatGPT. Oh crap.
Welcome to episode 1 of Programming Assembly Language for the Commodore 64 with ChatGPT. In this series, Mido will be using the Vice emulator to learn how to program in assembly language for the Commodore 64. ChatGPT, will be serving as Mido's guide and mentor, providing insight and guidance along the way. Let's get started and join Mido on this exciting journey of learning assembly language for the Commodore 64.
Okay. So since I accidentally had that muted, I'm going to play it again from the beginning, just so the VOD has the whole thing.
Welcome to episode 1 of Programming Assembly Language for the Commodore 64 with ChatGPT. In this series, Mido will be using the Vice emulator to learn how to program in assembly language for the Commodore 64. ChatGPT, will be serving as Mido's guide and mentor, providing insight and guidance along the way. Let's get started and join Mido on this exciting journey of learning assembly language for the Commodore 64. Episode 1 of the lesson plan is titled Introduction to Assembly Language and the Commodore 64. Here are the topics covered in this episode. Overview of assembly language programming and its history. Introduction to the Commodore 64 and the Vice emulator, setting up the development environment for programming on the Commodore 64. Assembly language programming is a low-level programming language that is used to program computers and other electronic devices at the machine level. Assembly language provides a direct and precise way to control the operations of the computer and access its hardware, making it a popular choice for system-level programming, embedded systems, and games. The history of assembly language programming dates back to the early days of computing, when computers were first being developed. In the early days of computing, there were no high-level programming languages like C or Python, and programming was done using machine language, which is a series of binary instructions that the computer can understand. Assembly language was developed as a way to make programming in machine language more accessible and easier to understand by using mnemonics and symbols instead of binary code. Over time, as high-level programming languages were developed, assembly language became less widely used for general-purpose programming. However, it remains an important tool for low-level programming tasks, such as working with embedded systems, writing operating systems, and developing device drivers. Additionally, assembly language is still widely used in the gaming industry, where it is used to write performance-critical code, such as game engines, and to create games for classic computers like the Commodore 64.
Okay, So my limited knowledge of ASM, such that it is, seems to agree with largely what I just heard. The only thing that I'm not sure about is I'm pretty sure that most engines nowadays are made in compiled languages like C and, well, it would be like C++, since it's more object oriented friendly than C. I don't really know that I've heard of a whole lot of mainstream using ASM anymore, but it definitely is still used in retro computing, as it says, which is part of why we're doing this experiment. Um, so, let's see. How did I phrase that? Okay, so I just say, tell me the.
The Commodore 64 is a home computer that was first released in 1982. It was one of the most popular home computers of its time, and it remains a popular platform for retro gaming and hobbyist projects today. The Commodore 64 has a 6502 processor and 64 kilobytes of memory, which was considered a large amount of memory for its time. It also has advanced graphics and sound capabilities for its era, which made it a popular choice for gaming and home applications. The Vice emulator is a software program that allows you to run Commodore 64 software on your modern computer. It is a highly accurate emulator that accurately reproduces the behavior of the Commodore 64, including its hardware and software. This allows you to run Commodore 64 software, including games and applications, on your modern computer without having to own an actual Commodore 64. This makes it a great tool for learning assembly language programming and developing applications for the Commodore 64. By using the Vice emulator, you can write and run your own assembly language programs on the Commodore 64, as well as run existing Commodore 64 software. This makes it an ideal tool for learning assembly language programming and developing applications for the Commodore 64.
Okay. So, once again, everything that I know seems to jive with what it said there. Not really sure what it's going to tell me here that hasn't already been done, since I did a little bit of pre-stream work, but we'll find out. Okay, we're going to do this in steps, so that'll be a little different than what we've been doing. Okay.
To set up the development environment for programming on the Commodore 64 using the Vice emulator, you will need to perform the following steps. Install the Vice emulator. You can download the latest version of the Vice emulator from the official website and install it on your computer.
Okay, and I did that, and that's accurate.
Create a new project. Open the Vice emulator and create a new project. You can do this by selecting File, greater than New Project in the menu.
So I do not see a new project, so I think this might be one of those times where ChatGPT is confidently wrong. It might be deriving that from other stuff where you have to set up your IDE, I would assume. Something like maybe Visual Studio. It's grabbing information from that. If anyone does know that I'm actually talking out my butt, by the way, feel free to tell me in the chat, and I will definitely read that. But I do not see an option for that, so I will disregard it. Or, should I correct it? That's one thing. I keep hearing people say that ChatGPT is so terrible because it can be confidently wrong, but I have a fundamental issue with that mindset because honestly, it has been my experience in life that any teacher can be confidently wrong. You know, a teacher can tell you that French is not a Romance language because there's that common mentality that French is a language of love. So to correct that, they say that it's not a Romance language, not knowing that Romance language has to do with its origin being from Roman. And a teacher can confidently say that. The reason that I don't think that ChatGPT is bad is because you can actually correct it. And it will, take in that information and adjust to it. It has been my experience that a human teacher never will let go of their firmly held beliefs. If you correct a human teacher, they will tell you that you are wrong. So I would almost say that this theoretically should be a slightly better teacher if it's got enough of the information available to it. So let's see. For step number 2, no such options exist in the file menu. Auto start disk tape image. There is still no option for that. There's smart attach, there's attach disk, attach diskette image, attach cartridge image. Now, so let's just assume that it's asking me to basically create a disk. So I did that ahead of time, so we'll just say that that's good. There we go. Don't really need that saying that the stream will start, because, hey, I'm talking to you guys right now, right? Okay, so let's see.
Write your code. You can write your assembly language code in a text editor and then save it as a file with a .asm extension.
Okay, so I don't actually have to enter the code directly into the vice if it's accurate. And I do wonder about that. I imagine, I had people telling me in the Discord for the Commodore 64 that you can use a text editor. So I assume this is accurate. I'm going to be doing it in the program though, just for that retro feel, right? Okay. Wow, come on, Google.
Assemble the code. You will need to use an assembler to convert your assembly language code into a machine-readable format that the Commodore 64 can execute. The Vice emulator includes an integrated assembler that you can use to assemble your code.
Okay. So, okay. I wish to write my code directly in the emulator using the final, was it called Final Cartridge 3? Um, yeah, Final Cartridge 3. Oh, well, let's try a refresh. Oh, that's handy. They just happen to be experiencing high load right now. Okay. Okay, I don't know why that. Why is my scroll wheel? There we go. Okay. So, don't think you select programming. Let's do a hard reset to see what that menu looks like, because I don't really remember. Okay. So, it says to select programming, which I do not see an option for. And I can't get the cursor to move again. Was it swap joysticks? No, it was not. Well, that was smart of me. Let's go back to symbolic. Maybe that has to be done. No. Oh, there we go. Okay. So under system, see basic. That's where I went before. Oh, that's interesting. There's a notepad built into Final Cut. Anyway, so let's just go back to basic. Wadoo. And there we go. We're at a basic prompt. That's interesting. It's got a much harder border than the default Commodore border. Okay, so that's the end of the episode 1 lesson plan, but honestly, I don't feel like we've done enough, so let's just merge episodes 1 and 2. So, let's see what it does if I say it that way. Wow, that's a lot of information it wants to cover. So, it seems like we already covered the overview of assembly language. Okay, the syntax might be a good idea. So let's go ahead and load this up into the TTS. It's a lot of information. Quite the information dump we got here. Let's see. Of course, it's going to take a bit.
Assembly language is a low-level programming language that provides a direct mapping between the machine instructions and the underlying hardware. It provides more control over the system compared to higher-level languages, but also requires a more detailed understanding of the system being programmed. The syntax used in assembly language is dependent on the particular architecture, but typically consists of the following elements: instruction format. Assembly language instructions are typically written in a mnemonic form, representing a specific operation that the processor can perform. Each instruction has a specific format, which may include an operation code, opcode, source operands, and destination operand. Register usage. Registers are special memory locations in the processor that are used to store data. Assembly language provides direct access to these registers, allowing you to perform operations with the data stored in them. Some common register names include accumulator, A, index, X, and stack pointer, SP. Addressing modes. Addressing modes determine how operands are specified in assembly language instructions. Different addressing modes allow you to access data in different ways, such as directly from memory, indirectly via a pointer, or as an immediate value. Some common addressing modes include immediate, direct, indirect, and relative. In assembly language, instructions are written in a specific format, with the operation code and operands separated by spaces. The syntax may vary slightly between different architectures, but the basic elements of instruction format, register usage, and addressing modes are common to most assembly languages.
So that was the syntax, right? It also just covered the register usage. Or wait, demonstrate how to use the registers in Commodore 64 to store and manipulate data. Okay, so that we'll have to do. So let's just, yeah, I'll have to remember to scroll there. I really wish Enter would send. Yeah. So, from what I understand, from what it was just talking about, so you have your opcodes, which is going to be your stuff like LDA and STA, which are respectively load and store, I think, into the accumulator because they have the A, and that then is the register that I was talking about, I would imagine.
In assembly language, the registers are special memory locations within the processor that are used to store data. The Commodore 64 has several registers that you can use in your assembly language programs, including accumulator. The accumulator is a general-purpose register that is used for arithmetic and logic operations. It is the most commonly used register in the Commodore 64, and is used for both the source and destination of many operations. Index register X. The index register is used for indexing and pointer arithmetic. It is often used to hold the address of an array or the offset of a data structure. Index register Y. The Y register is similar to the X register, and is also used for indexing and pointer arithmetic. Stack pointer, SP. The stack pointer is used to keep track of the top of the stack, which is a last in, first out, LIFO, data structure used for storing temporary values and return addresses. Program counter, PC. The program counter holds the address of the next instruction to be executed. It is automatically updated by the processor as the program executes. In your assembly language programs, you can use these registers to store data, perform operations, and control the flow of execution. For example, you can use the accumulator to perform arithmetic operations, such as addition and subtraction, and you can use the index registers to index into arrays and perform pointer arithmetic. The stack pointer is used to manage the stack, and the program counter is used to keep track of the current instruction being executed. It is important to understand the usage of these registers, as they play a central role in assembly language programming, and their proper usage can greatly affect the performance and functionality of your programs.
Okay. So let's try asking a question about this and see what it says. I've already verified that the pointer or the registers that it mentioned all do seem to exist. I'm on the C64 wiki. There's the stack pointer, the X index register, the Y register, and it also says Y index register and X and whatever, and then the accumulator. So it actually mentions X and Y twice. Once as the index and once not as the index. So there might be something that I'm not quite understanding there. But we will find out as we progress, hopefully. But let's try asking a question. Just delve into its greater understanding. Are these same registers used on the NES? Since it does have a modified 6502, it's not the stock 6502, maybe the registers are different. That's good information to have, since part of the goal of this series in the long run is to actually see if we can't port an NES game that has released source code to the Commodore 64, with modifications, probably, since there's some major differences between the hardware. Oh, okay, so the Commodore 64 uses a 6510. I didn't realize that. I thought it was 6502 as well, which, once again, that's one of those confidently wrong things. I actually, when I was talking to ChatGPT to plan this, ChatGPT even said that it had a 6502. But looking over here, it does, in fact, the article that I'm looking at does specify that these are the 6510 registers. The NES, though, let's see, has the accumulator, the index register X, the index register Y, the stack pointer, and the program counter. So it seems like it does have the same registers, but it's saying that because they're not the same processor, they might be different. Similar to the Commodore 64, similar to the Commodore 64, similar to the Commodore 64. Yeah, okay, so it's just giving a little bit of wiggle room since they're not identical processors. Now that's actually nice to know. That'll, if they both have the same exact 5 registers, that's going to simplify the porting of code, since at least the register stuff we won't really have to mess with. We're going to have to mess with memory maps and crap like that, but the registers themselves, the LDA and stuff, will pretty much stay the same, I think. So let's see, episode 2, addressing modes. So let's see. So let's go ahead and actually load this up so we can listen to it.
In assembly language, the way in which you access and manipulate data is determined by the addressing mode you use. The addressing mode specifies the location of the operand used in an instruction. There are several different addressing modes used in assembly language, including immediate addressing. Immediate addressing mode is used when the operand is an immediate value, such as a number or a character constant. In this mode, the operand is encoded as part of the instruction itself.
Okay, so that I think it's saying that like LDA, we don't tell it what to do with that data; it just does it. We don't have to give it an address or anything like that. It just we tell it LDA and it loads A.
Direct addressing. Direct addressing mode is used when the operand is located at a specific memory location. In this mode, the instruction specifies the address of the operand directly.
Okay, so this one we give the operand whatever it might be. I don't know enough operands to guess which ones might have addresses, but say store, right? We want to store a value that's currently in the accumulator. We would need to store that at F372, for instance. So we would give it that memory address, and then it would store the information in the accumulator to F372, I think is what I said. So that seems to be what direct is. We put the operand, then we put the address, and then it does the job on the address.
Indirect addressing. Indirect addressing mode is used when the operand is located at the memory location specified by a register or memory location. In this mode, the instruction specifies the address of the register or memory location that contains the address of the operand.
Okay, so with this one, we might give it an address, but instead of just doing the operation on that address, it will go to that address, check the information there, load that into its operation, and it'll use that as the address where it performs the action. Good for if you need variables, I guess.
Each addressing mode has its own advantages and disadvantages, and the choice of addressing mode will depend on the specific needs of the program being written. By understanding the different addressing modes and when to use each, you can write more efficient and effective assembly language programs.
Yeah, okay. Back to the lesson plan. I feel like I overshot. Yeah, okay, here we go. That was the addressing modes. So now basic instructions. Demonstrate how to use basic assembly language instructions such as load, store, move, and compare. Okay, so she's actually going to be giving us some code information, it looks like.
Basic assembly language instructions are the foundation upon which all other assembly language programs are built. These instructions include load instructions. Load instructions are used to load data into a register from memory. For example, the LDA instruction loads the accumulator with the value stored at a specified memory location.
Okay. So say Mario gets hurt, right? We need to subtract his HP. So we would LDA on the address that stores his health. Then we would perform arithmetic on it while it's still in the accumulator, I believe. And then we would then use the next one it's going to be telling us about, the STA, to then store that back into the right memory address.
Store instructions. Store instructions are used to store data from a register into memory. For example, the STA instruction stores the contents of the accumulator into a specified memory location. Move instructions. Move instructions are used to copy data from one register to another. For example, the tax instruction moves the contents of the accumulator into the X register.
Okay. I wonder if you need to do that to perform arithmetic, or if you can perform arithmetic directly on the A register. I suspect you might actually have to move it into the X, because otherwise you only have the one data set to work with. You can't subtract 13 from 21 if you only know 21. So you have to store that 21 into another register, then load the 13, and then you can subtract it. I think. This is part of the learning process.
Compare instructions. Compare instructions are used to compare the contents of two registers or memory locations. For example, the CMP instruction compares the contents of the accumulator with the value stored at a specified memory location.
Okay, no, this actually contradicts what I was saying before, because it can do something with the accumulator and a memory address. So we probably could do arithmetic using the accumulator and a memory address. But anyway, back to the compare. So this is going to be, I think, the equivalent of ifs, basically. So we're going to need to compare values to see which one's greater, if they're equal, which one's less than, etc. And I think this is going to be our way of doing that. And then we can then act upon the comparison after the fact, I think.
These basic instructions form the building blocks for more complex assembly language programs. By learning how to use these instructions, you can begin to write simple programs that perform basic tasks on the Commodore 64.
Okay. Arithmetic. I was actually just talking about that even. Looks like she'll be explaining a bit of arithmetic to us.
In assembly language, you can perform a variety of arithmetic operations to manipulate data. These operations include
Additions that go to given.
addition. Addition is used to add two values together. For example, the ADC instruction adds the contents of a specified memory location to the accumulator.
Okay, so it's not the subtraction, but it's similar. Say we wanted to increase your health from 13 by 13, right? So you would store the first 13, which is what the health value. Okay, you would LDA the current health, which is 13. So now the register holds that 13. Then you would ADC the memory address for how much health you're gaining, which would register another 13. And then the result would be that the accumulator would now have 26. And then you would just do an STA on the memory address where health is supposed to be stored, and now the health is 26. Subtraction obviously is going to do the reverse of that, so if we want to deal damage, we can.
Subtraction. Subtraction is used to subtract one value from another. For example, the SBC instruction subtracts the contents of a specified memory location from the accumulator.
Okay, and yeah, just the exact same thing. We LDA the health, we SBC the damage, and then we STA the health. And that will give us the changed health.
Multiplication. Multiplication is used to multiply two values together. On the Commodore 64, multiplication is typically performed using a combination of shift and add operations.
Okay, so we don't, it sounds like on the Commodore 64 we don't have any instructions that actually can do multiplication. Instead, we have to kind of duct tape it like they did back in the day. Now shifting, she's not explaining that. I don't know if she will, but fortunately I happen to already know to a degree what shifting is, and it just means that you're moving the bits left and right. But I hope that she does actually explain that in better detail as we go. I suppose that right now, if I know nothing about it, I could ask, what is a shift operation? And I probably should.
Division. Division is used to divide one value by another. On the Commodore 64, division is typically performed using a combination of shift and subtract operations. These arithmetic operations form the basis for more complex mathematical calculations in assembly language. By learning how to perform these operations, you can begin to write programs that perform more advanced tasks on the Commodore 64.
Okay, so let's ask her about those shift operations, right? So what is a shift operation? I don't know how I spelled that wrong. Let's just steal it from her. Okay, so what is a shift operation? And one really cool thing about ChatGPT is that it's taking into consideration everything we've already talked about. Now, I've noticed that at times it seems to kind of forget what we've talked about, but it still usually is close to the mark.
A shift operation is a basic operation in computer architecture that shifts the binary representation of a number to the left or right. This operation effectively multiplies or divides a binary number by a power of 2.
Yeah, okay. So basically what I said,
there are two types of shift operations: logical shift and arithmetic shift. Logical shift. A logical shift moves the bits of a binary number to the left or right, discarding the bits that fall off either end and filling in the vacant positions with zeros.
okay, so whatever, let's make it a smaller bit number so that it's easier to kind of digest. So we've got 1011, right? If we shift it to the left, we will have 0110 because we just got rid of that 1. It just doesn't exist anymore. So we shifted everything to the left, so that 0 in the hundreds column moves to the thousands column, etc., etc. All of them move left 1, gaining a positional value of 1. So it goes from 1011 to 0110.
Arithmetic shift. An arithmetic shift is similar to a logical shift, but when bits are shifted to the right, the sign bit is replicated in the vacant positions, preserving the sign of the number.
So when shifting to the right, the sign bit, which we still don't know, so I should probably ask her to explain that, but that sign bit gets replicated, it says in the vacant positions. So it sounds like the sign bit is following the number, but there has to be a way to know that it's the sign bit, not one of the number's bits. So I'm not quite sure how that works. So we will ask for information about the sign bit. Oh, I just pasted that in the wrong place.
Shift operations are frequently used in computer arithmetic, particularly in multiplication and division, and they can be performed more quickly than traditional arithmetic operations.
Yeah, I suppose that it would be pretty easy. It's basically like running a number through a shift register. You know, just pop, 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 pop. The numbers just slide to the left or to the right. There's no actually having to think about how to modify it. So let's ask about that. What is a sign bit?
A sign bit is a bit in a binary number that represents the sign of the number, either positive or negative. The sign bit is typically the most significant bit, MSB, of the number. Where a value of 0 represents a positive number and a value of 1 represents a negative number.
Okay. We can go ahead and just do the last two paragraphs all at once now that they're all loaded.
For example, in a 8-bit binary representation of a signed number, if the sign bit is 0, the number is positive, and if the sign bit is 1, the number is negative. If the number is positive, the remaining 7 bits represent the magnitude of the number. If the number is negative, the magnitude is represented using 2's complement representation, which involves flipping all of the bits and adding 1 to the result. The use of a sign bit allows binary representation of signed numbers, which are numbers that can represent both positive and negative values. This is in contrast to unsigned numbers, which can only represent non-negative values.
Okay, so one thing that, a complete beginner student would be asking is, what is the MSB? I know vaguely what it is, but I always forget how it works with the most significant, least significant. My interpretation always, or my instinct always, is to say that most significant is effectively the first bit, because when we look at a base 10 number, the numbers that we deal with in everyday life, the first number, the millions digit, first say, is the most significant. It's the largest. It's the digit that carries the most value to it, because it carries a whole or we said million, right? It carries a whole million bits of information to it all by itself. That one decimal point does. Then the 100,000 carries 100,000, so it's less significant. That's how I interpret it. But I might be remembering it backwards. So let's ask her what's the most significant bit. But it will either be the first or the last bit. Alright, so leftmost, just like I was saying, but let's pop this into text-to-speech just to hear it out. rather than just seeing a word that confirms us and then saying, hey, we know.
The most significant bit, MSB, is the leftmost bit in a binary number representation. It represents the largest value in the binary number and has the greatest impact on the decimal value of the number. For example, in an 8-bit binary number representation, the MSB is the leftmost bit and has a value of 128 in decimal. If the MSB is set to 1, it indicates that the number is negative if the binary representation is being used to represent signed numbers. It's important to understand the significance of the MSB when working with binary numbers, as it can greatly impact the value of the number and determine whether it is positive or negative.
Okay. And now we've kind of chased down all those little hairs that someone might not know. And it's nice to see it. It literally does confirm my mindset. Now, once again, one thing that we have to be very careful of is it's confidently wrong. But since it sounds good enough, we're going to roll with it because that's what a noob would do. Okay, we've answered all the questions and everything sounds good, so let's just keep going. And if we end up in a rabbit hole, well, we end up in a rabbit hole, and so would a noob. So that's important information for us. Here we are. So that was the arithmetic, right? So now we need the jump instructions. And this is the subroutines. And we still haven't learned any code.
Jump instructions are a fundamental aspect of assembly language programming and are used to control the flow of execution in a program. These instructions allow you to branch or jump to a different part of the program based on certain conditions.
Yeah, so once again, similar to what I was saying about the compare operation, these are going to be very important in replicating the effects of an if. So, if X is true, well, we need to do something if that happens, and that'll be when we'll jump. We will jump to the code that executes if it's true, or else we'll jump to the code that executes if it's false. Now, how we know where to jump, that's probably going to be described below with the BEQ and stuff like that, which is branch if equal. I already know that one. I've heard that one before.
Jump instructions typically include conditions, such as whether a certain value is equal to 0 or greater than 0, and they allow you to specify the target location to jump to. The target location can be specified using an absolute address or a relative offset.
Okay. That's interesting. So, you don't have to jump to F13.7. Yeah, you could just jump forward 8 addresses. But it's not saying that that's true in Commodore, so we need to be careful of that. It might be that some assemblers can do that, but some can't.
Here are some common jump instructions that you may encounter when programming in assembly language.
So we got jump, we got branch if equal, we got branch if not equal, we got branch if greater than, and branch if less than. They're, to anyone with any programming experience, even meager programming experience, these probably sound very logical. Jump is just if you want to go to a different point in code. It's like calling a function almost. Or in BASIC, it's a go-to operation. Now, branch if equal, that's literally just when you say if A equals B. If they equal, then you go to this line of code. If they don't equal, then you go to that line of code. BNE, branch if not equal, that's literally just the opposite. So that's if you add an exclamation mark to your equal operation in the if that I just described. Branch if greater than, and it actually says here that it's relative to a specified register. So that's going to be why you're going to use the equal or the not equal, is because you need to be working with information in your register, which will probably be our accumulator most of the time. So we have a number in our accumulator. We need to test if this memory address has the same value as what's in the accumulator. If so, we'll talk about the EQ, right? If they are equal, then we go to the true address. If they aren't equal, then we go to the false. BNE is just the opposite. It's the opposite logic table. Branch if greater than, if the number, I'm going to assume if it's the number in the memory address is larger than our accumulator. I will actually play the audio for all of these after I've made my assumption, but just given my assumption real quick. Then we got the branch if less than, and it's literally just the greater than reversed. So let's go ahead and give a listen to the audio and see what she has to say.
JMP, jump. This instruction unconditionally jumps to a specified target location. BEQ, branch if equal. This instruction jumps to a target location if the value in a specified register is equal to 0. BNE, branch if not equal. This instruction jumps to a target location if the value in a specified register is not equal to 0. BGT, branch if greater than. This instruction jumps to a target location if the value in a specified register is greater than 0. BLT, branch if less than. This instruction jumps to a target location if the value in a specified register is less than 0.
Okay, so clearly what I was saying a little bit off, because we can't compare to a memory address. But with a little bit of arithmetic, we can. So let's say we use the subtract operation that we learned about a little bit ago. First, if we subtract the memory address from the accumulator, well now, if we do a branch if equal, well if it's 0, then the two numbers equal each other. BNE, if it's 0, then they equal each other, so you register that as a false. Now, interestingly, if they do equal each other, then you don't jump to a second memory address for that. No, you just keep going in order. So it's only good for deviating. It's not good for, like, splitting your path, per se. You would have to use a BEQ followed by a BNE if you wanted to jump to different parts of the code for both answers. For branch if greater than, once again, if we just subtract the value of our information, well, if it's less than 0, then we know that the accumulator was less than what was in the memory address, and vice versa with the BLT. So, we can do a decent amount of stuff that you would use ifs for with this stuff. It's not really at all a bad deal.
By using jump instructions, you can create complex and dynamic control structures in your assembly language programs, allowing you to make decisions and take actions based on specific conditions.
Yeah, and you wouldn't even have games if you couldn't use jump instructions. Because, yeah. Actually, would we really be able to do anything we do nowadays without jump instructions, really? Probably not. And now we got subroutines. let's actually do the a la carte way, because then we can like discuss between paragraphs.
Subroutines are a key concept in assembly language programming. They allow you to write a piece of code once and reuse it multiple times in your program. A subroutine is a block of code that performs a specific task and can be called from multiple places in your program. When a subroutine is called, the program execution transfers to the first instruction in the subroutine. After the subroutine has completed its task, the program execution returns to the instruction immediately following the subroutine call.
Okay, so subroutines effectively are what we would call functions in more modern compiled programming languages. For instance, you're playing Mario, right? And you take damage. You don't want Mario to then be teleported to the first place that he could possibly take damage, but you also don't want to replicate that damage-taking code everywhere in the whole game. So instead what you do is you write a subroutine. That way, anywhere from the game, you can execute that subroutine to make him take damage, and then jump right back to executing the main code again. Here's how subroutines work in assembly. Let's just go ahead and load in the whole list.
Subroutines are a key concept in assembly language programming. They allow you to write a piece of code once and reuse it multiple times in your program. A subroutine is a block of code that
Okay, we already covered a lot of that. Let's backspace that, and then
write the code for the subroutine. The subroutine is written like any other code in your program, with a sequence of instructions that perform a specific task. Label the start of the subroutine. A label is used to identify the start of the subroutine in the code. The label can be any unique string of characters, but it must be followed by a colon. Call the subroutine. To call the subroutine, you use a JSR, jump to subroutine, instruction, followed by the label of the subroutine. When this instruction is executed, the program execution transfers to the first instruction in the subroutine. Return from the subroutine. After the subroutine has completed its task, it returns to the calling code using RTS, return from subroutine, instruction. This instruction transfers the program execution back to the instruction immediately following the subroutine call.
okay. So we have to write the code, and that's true of any programming language you might have. In BASIC, you got to write the code. In C, you're gonna need to write the code, etc., etc. Now then, where things start to deviate. So you got the label. That's the start of your code. In assembly, it's just that. It's a label. You get the same thing with BASIC. You got your labels. I'm sure anyone who's got any experience with writing BASIC has used labels. And then you can go to label instead of going to a number. Then again, maybe that's not anyone. I know that my old Logic computer, as well as the DOS computers that I've programmed in BASIC, all had label support. I don't know if, like, a lot of the 8-bit computers do, though. That's something I'll have to try learning at some point, because I really should learn the more vintage basics. But yeah, you got a label. Oh, Batch has labels, so anyone who's done Batch has probably experienced labels. And then you can go to that label. The calling the subroutine, that's literally, I keep saying go to. In many languages, that's literally what's called. Now, if we were going to compare it to an object-oriented language like C, instead it's going to be where you call the function. You put the name of the function with a parentheses, and then maybe any variables you want to pass to it, and the end in a semicolon. And that's when you call it, and then it jumps back to where you're at. The return well, once again, when we're talking about C, you would have somewhere in your block of code for the new function a return, and then you can have it return a value that we can pass variables back to the function. Now, the passing variables back and forth, we probably can't do in assembly. Instead, what we probably need to do is like move it into the accumulator or move it into memory addresses. But that's not terribly the end of the world. This, we already know going into this, we're a lot closer to the processor's own language, so things need to be done in much more robust ways. So you can't just send variables into a subroutine, a dozen variables into a subroutine, and then receive a dozen variables back from the subroutine. Instead, what you need to do is move variables to a specific place in memory, jump to the subroutine, have the subroutine access those memory addresses, and then jump back. And it's, once again, that's not too terrible, but it's just what you expect, because like I said, we're dealing with the processor down on its level, basically.
By using subroutines, you can simplify your code and make it easier to maintain. You can write reusable pieces of code that can be called from multiple places in your program, reducing the need to duplicate code and making it easier to modify the code in the future.
And then so subroutines, that was everything. Ah, dang it.
By the end of this episode, you will have a solid understanding of the basics of assembly language programming, including the syntax, register usage, addressing modes, basic instructions, arithmetic operations, jump instructions, and subroutines. This knowledge will lay the foundation for writing more complex programs in future episodes.
For writing more complex. So should we already be doing our hello world? Let's actually ask her, because if in class you're already on the second day and you hold up, the teacher goes through everything, you got the whole lecture done, and you still haven't done any homework, you still haven't written a single line of code, you're gonna hold up your hand and you're gonna be like, hey teacher, should we write a program like a hello world or something? And then you'll find out. So let's ask her. Or should I? Now we gotta remember, we now have to say an episode later than what it is, because we're still in the first episode, but we did episode 1 and 2 at the same time, so now we gotta say episode 2, even though we're only recording episode 1. And that's simply because episode 1 was kind of lackluster as far as content goes. It would last like 15 minutes. Let's see what she said as an answer.
By the end of episode 2, you should have a solid understanding of the basics of assembly language syntax, register usage, addressing modes, basic instructions, and arithmetic operations. With this knowledge, you should be able to write a simple program such as a hello world program on the Commodore 64. It's important to keep in mind that programming in assembly language takes practice and patience, so don't get discouraged if it takes some time for the concepts to sink in. Keep working through the lessons, ask questions, and keep practicing, and you will get there.
Okay, so I'm trying to think, do we actually have enough information? She says that we should. And I mean, fundamentally, I understand enough of the concepts that I could write I can theory craft what this program would look like. So we're gonna LDA out of the character H. And then we can STA that into a memory address associated with the screen memory. And then we do the same for E, the same for L, L, O, you get the point. You know, so we just LDA it out of the character, and then we STA it into the screen. But we don't know yet how to start making a program. You know, I can open up the Commodore right now, and some people explained a little bit of the concepts to me already, so I know in order to start writing assembly, I type mon. Now we're in the assembler. Do I just type LDA and then put an H in quotes, hit enter? Well, I mean, I maybe can, and maybe it'll run, but we're not going to get a program that exists in a place in memory if we do it that way. You know, like, think about BASIC, right? We got to tell it line 10, and then it stores that at line 10. We got to tell it line 20, and then it stores that at line 20. Well, we got to tell this, where are we going to store our program so we can then execute it, and then edit it, and then save it, you know, etc. So we need to tell it where to start. Then we need to give it all the instructions, yada, yada, yada. And then we also need to know what are the memory addresses for the screen. She didn't tell us that. We can look that up, obviously, through Google. I actually have a picture ready to go for that. Here's the memory map, right? Only problem is that none of this looks like it's going to be storing the visual memory, right? So which addresses associate to the video memory? It doesn't seem like any of them do. So I could do more deep looking and probably find those addresses. I bet that Google will find it like that, but she hasn't taught it to us yet. So the statement that we should be able to make a hello world, I don't think it's quite true. Like I said, we can theory craft it, but I don't think that we can make it. No. So let's say, how would I start creating the hello world program, right? Because you can ask a teacher, right? She basically just said, hey, you can do hello world. So okay, now we ask, okay, how do we start? Because we feel like she didn't give us information. Oh, and here she's giving us a wow. I actually wonder if the Commodore 64's built-in assembler can handle comments like that. That's an interesting thing to wonder. Anyway, so here's an example program. So set up the screen and color memory. Once again, we're not telling it where to start, right? I think that if I type this LDX, that's supposed to be an L. Whoopsies. So LDX should be 00. Okay. It doesn't even know. So LDX doesn't seem to be an opcode that it supports. Commodore 64 ASM does not seem to support LDX. Right? So let's see what she says. Yeah, it doesn't have the load X instruction. Instead, you would use the load A instruction to load data into the accumulator register and then use the tax transfer A to X instruction to transfer the content to the accumulator. Okay. So, instead we LDA this, right? Oops. That still isn't happy. Well, let's assume the accumulator has that value in it now, right? So now that the accumulator theoretically has it, we do a TAX. TXS. See, it's doing that. LDY, which it's not going to be able to LDY. So we're going to have to do LDA $, D020. TAY, we'll just assume that's the thing. And then STY. Oh. Actually. STA. We'll just STA it. $, D020. And STA $D021, which I'm not even sure why we were writing the same value to two different memory addresses. But yeah, so it says set up the screen and color memory. Nothing's changed. So clearly we're not doing something right in writing the program. If I do an R, the registers don't seem to have changed. I think I was told these are the registers. I'm not sure. But yeah, nothing has changed. So oh, this actually says it's in 6502 assembly even, which weren't we told this is the 6510? That's an interesting thing. Yeah. So yeah. I'm not exactly sure if we're at a spot where we should be able to code and it's just that ChatGPT has actually majorly dropped the ball, or if we just need to keep plugging through and check out episode 3. That said, we've been at this stream for an hour and a half. I'm gonna be calling it a day, I think, and then pick this back up in a week. No, that. So here's the problem we have. I can wait a week, and this stuff will become a little rusty. I might have to do a quick review, or else we can do this again tomorrow, and it'll be a lot fresher. But we're gonna have a kid running around. So if anyone's watching and doesn't like the idea of a kid on the stream, being able to barge in on the stream, let me know. I will be watching chat. If no one says no, I'm probably just going to make do with that because it does seem better for the learning process. I'm not sure what YouTube's delay is, so I'm just kind of killing some time. Okay, considering that everyone I advertised to was on Discord anyway, if you want, you can DM me. So we'll find out. I will catch y'all on the next episode.